All right, so welcome everyone. We're thrilled to have you join us for this community tech session where we're going to deep dive into networking for AI/ML workloads. It's a topic that's not only critical to, say, modern infrastructure, but also deeply relevant as AI continues to reshape the way we work and build. Our speaker today is someone who brings both depth and breadth of expertise in this space. Please join me in welcoming Bhargavi. She's a senior technical lead at Cisco who has 2 decades of industry experience designing and developing various networking products. She's a seasoned data center networking expert with key contributions to SAN fiber channel, FCOE, and ACI technologies. She has led teams in designing and implementing SAN features on Cisco MDS and Nexus switches, ensuring reliable server-to-storage connectivity. Her deep expertise spans network layers, hardware diagnostics, packet forwarding, and protocols across a range of core switches, routers, and FTTU products. A passionate developer with creative problem-solving skills and a great mentor, she has emerged as a strong technical leader, leading teams to successfully design and implement numerous end-to-end projects with unwavering team spirit. I think we're in for a good learning session, so let's dive in. Over to you, Bhargavi.
Thanks a lot for the introduction, Karen, and welcome you all to the session. Thanks for attending and being part of today's learning experience. As you all know, today's topic is networking for AI/ML workloads. So a few years back, I think internet was the boom, and it was internet everywhere. And now we are at an era where it's AI everywhere and on everything also, right? It's no more AI is no more in the labs for scientists to work with. It's on the internet for all of us to consume, and especially after GenAI and things like large language models coming in, it's there for even the common man to start using it, right? But have you ever wondered how is it all possible? How is it coming on the internet? How are the models, and how are we able to train it and inference the models on the internet? So myself, Bhargavi, and with the introduction that's given by Karen, I have a deep expertise in data center. And in this session, we will be going through the basics of data center, just overview so that we are all on the same page. And then I'll also see how AI/ML as a model, and what's the requirement as a model. And then let's connect the dots and see what is it with data center and AI/ML models, right? So before I get started, I want to know how many of you are familiar with the data center and with the life cycle. So whenever I have questions like this, in the poll will pop out. Please respond and let me know what's your take on these two things so that we can build the topic and based on your where the most of the participants stand. So Karen, let me know when you stop the poll, and how do I view the results?
Yeah, just give me a second. I'm just giving everyone some time to answer.
Sure.
It seems like a 50-50.
Okay. And how about for the other
it's a 50-50 between a rating of 9 and a rating of 4.
No, I think that could be me. How many of them have answered?
We have 25% participation only, though. I think people are either on their phones or...
Okay. Okay. Yeah. Well, assuming that most of you are on a middle scale about it.
Yeah.
So let's get into the details. Okay. And please feel free to post your questions, and we can also have a Q&A session at the end for about 5-10 minutes and get into it, right? Okay. So just about data center. So if I have to put data center in just a line, is something, a center where data is processed and we're working with data, right? And AI is basically all about data as well. So what happens and what's there in the data center infrastructure? These are the three pillars. You just have to remember the three pillars or the three main blocks of data center. It's compute, where the data is processed, storage, where the data is stored, and network, where we are interconnecting the servers and the storage and also connecting to the external network and having all of these data move across. So that is data center in short for you. So if I have to show it in the network topology, where does a data center fit in? This is your LAN network, or it could be your internet for that matter. And let's say you're all sitting here trying to access a Facebook page or something. So it all comes down from the internet to the data center. So this is where my data center onto the down of LAN, right? Below the LAN, this is where my data center is sitting. So it comes to a Facebook server, and Facebook server in turn may ask a few other servers for authentication and other data that it could be in the storage devices itself. So we have a lot of, before one request of yours on Facebook page is processed, we have a lot of communication happening between the servers. That happens through the data center switches, and it's also happening between the server and the storage devices, right? So this is what is happening in data center. And then the data that is processed, or the data that you were looking for, is sent back to the the requested client. Now here, the traffic between the client and the server is called as a north-south traffic because of the direction of where the traffic is flowing. And the traffic between the servers and the server and the storage devices is called an east-west traffic. The earlier days, where it was just like a simple HTML page or static pages that was there, the traffic between the servers and the storage devices weren't more. It wasn't more. It was mostly north-south traffic. But over the advent of a lot of things, there's processing that's happening, huge amount of processing also happening. We have server-to-server traffic, and that is the east-west traffic increasing over the decades. Now, this is how we would connect internally in a data center. This is how you could connect the servers and the storage devices. The storage devices, the servers usually use Ethernet and network switching, and the servers can access the storage devices using a special fiber channel switch, and that's where I've been working for a decade on. It's called storage area networks. Or you could also have the same, you could have a converged switch which can talk both Ethernet as well as, it's called FC, so fiber channel protocols, or it could be a converged network. So this is different way of deploying my data center and the data center switches, right? So this is just brief, just to keep you all on page. What does data center mean? So let's have a quick quiz, and most of the quizzes here are just to keep the audience engaged, nothing very deep technically. So let's have the quiz. And I request each one of you to participate so that we know, we are following the session. So what are the three pillars of data center? Compute, storage, network, compute, server, and storage, network, switch, and firewall, or storage, network, and switch. So Karen, let's say we get 30 seconds or 20 seconds. Yes, so we have 6 or 7% saying compute, storage, and network, and 33% saying compute, server, and storage. So the correct answer is compute, storage, and network, while server is actually a part of compute itself. So the three pillars would be compute, storage, and network. So let's move on. Let's move on to bring in the other concept of today, that is AI ML, right? So the way it has evolved, it all started with artificial intelligence. It used to be called fuzzy logic back when I started my engineering. I started building upon as AI, artificial intelligence, and a lot of ML models came in for the deep learning, and now we are days of generative AI, right? So this is the complete landscape that is happening, and I'm assuming most of you have an idea, fair idea about the AI, different types of AI itself, right? There's more so we used to have predictive things coming, predictive analysis and as part of machine learning, but with generative AI we can generate new content. It's just not limited to prediction now. It can generate different content, and I think it's a very, very nice time to be, especially, and there's a lot of things, a lot of possibilities around this. So let's just look at the internals, right? Because how do I relate it to network? What's in it for network and AI? And that's where I want to just get into the internals. So whenever we're talking about a model, either it's a machine learning model or a Gen AI, LLMs or whatever, right? What are we talking about? We have a lot of data that is going to be captured, and we develop a model based on the data that we have. Different algorithms are tried, and we start training the model, right? So that is what is called as a training phase, a very important phase where all these data is taken, and the model goes through an amount of training. And the next, after you've trained, you deploy the model and you start inferencing. That is where the prediction or the generation of the things that happen at real time. And there's also a concept of, a retuning, whereas based on the inference that is done, if there is some amount of feedback that needs to go back, there's a retraining that happens, and that's where you have a personalized, or you could also take like what's happening in GenAI, right? You call it as RAG. That is, there is a context-based learning, or a more specific learning based on some of the proprietary stuff, or the very industry-oriented concepts. So that is how the entire model or life cycle of an AI model works. And if I might go back, and I think people who have started learning AI, or who are into the AI cycle, this figure is the most commonly seen, right? For any models that we talk about, let's say as simple as supervised linear regression model, we are talking about a stream of inputs, and then there's a hidden layer, and then there's an output. So the model is going to give you a function of, so X is a function of Y, and what is that function? Is it a square root? Is it a square? Is it a cuboid? Whatever, right? Simple when we talk about this. But in AI, I mean, I'm just trying to way to simplify it, but there's a huge amount of maths involved, right? So input and a function of the input variables, and there could be a lot of parameters. When I said X, this could now scale to trillions. I mean, I think billions and trillions of parameters is what LLMs now have. So we are talking about this, but at the end, they all boil down to metrics and vector multiplication and metrics, right? So in AI as such, there are two phases. One is a training phase, where you give a lot of data, you take the model, you optimize the model, and then you train it so that the hidden layers, the parameters, and the function is now determined by the model. And once you've trained the model, you deploy it for inferencing. That's when you test. That is, you give 10 pictures of a dog, train it to say that this is how a dog looks like. And then you give a 11th picture to it and ask it, is this a dog or not? You're basically asking it to infer it. So that is what the inference is. So there's two phases, training, and there's another phase called inference. Now, let's try to connect the two. How does AI model and how does networking or the infrastructure connect? So this is how the entire big picture looks like. So in my data center networks, I'll have the models getting trained. And let's see in the next sections how they are actually trained. What are the infrastructures, or what are the components that are involved in this training? So how are these models trained? That is what is happening in your data center. And once the model is trained, the model is deployed. It could be deployed on edge. It could be deployed in the data center itself, or it could be on the cloud. And now a user is trying to request, it's trying to inference. It could, right, and to predict something based on the model, the predicted inference or the generated inference goes to the user. And there is also a feedback mechanism so that you can retrain the model. So, and this is where we are connecting the AI models with the data center or the networking infrastructure, right? So now, as I said, there are three pillars to the data center, that is servers, storage, and networking. So in aspect to AI ML, let's see what kind of servers or compute is there and how is the networking happening and what kind of storages are available, right? And this being just a 1 hour session, I'm just going to touch upon each of the topics to understand the landscape that's there in the AI ML infrastructure. So we'll not be deep diving into any of these things due to time constraints, but each one of them is a topic by itself. So quiz time. I hope everybody is on the same page as I am and are following. So let's start the quiz. Which of the following is not a processing unit? And I'm afraid by the time you answer, one of them may actually turn out to be a processing unit as well. So, these days we have huge amount of processing units. Okay, so can we have the answers? CPU, DPU, FPU, and GPU. So 67% think that it is DPU and 33 think that it is FPU. And the answer is FPU as of today. The others we do have. So central processing unit, DPU is data processing unit. That's highly nowadays used both in AML as well as security for specific data processing. And we have GPU that we'll be talking today, the graphics processing unit. Okay. So graphics processing units. So NVIDIA back then started GPUs for their gaming applications and graphics. That's how it all started. And this is basically specialized for parallel computing. When I say parallel computing, let's take an example of what it means. So let's say I want to build a car, and what if there's just one machine which does all of it? That is, makes the engine, makes the body, makes steering, gearbox, and all of those, and then tires, and then assembles it. If that's the process that you would be following, that is serial, just imagine what the kind of machine that you had to actually develop to do all of these tasks, plus the amount of time that it would take, right? So that's exactly what CPU does, serial processing and, all one by one. But if that wouldn't scale, for I do, let's say vector multiplication, I do A plus B, and then again I do C plus D, and then I multiply those two things, it's going to take forever. So now instead, let's take the car analogy again. Let's say we have one machine doing the gearbox, the other machine doing the engine, there's another one doing the body, and finally it all goes to a CPU kind of a thing, right? Where we assemble it. So that's exactly what we're doing in GPUs. We're splitting the task and doing each one of the GPUs is doing the same repeatedly, same computation repetitively. And then finally, we are collecting all those information and getting the final output. So this is where you're training. That's how you're training with lots and lots of GPUs and lots of cores in each of these GPUs, performing those computations parallelly and then collectively assembling them, right? So that is where your GPU comes into picture. And now, as I said, GPUs were initially for graphic cards, for graphics. So graphics, if you think graphics or video games, is basically pixels, and pixels had to be represented by different numbers for each colors and brightness and all of it. And it very it kind of was very close to a matrix multiplication, if you remember. So where you are multiplying the rows versus columns and then all adding up, right? So that is where it all came, that we can use GPUs for AI ML as well, but with an extra accelerator, that is an extra hardware device that is more customized to do HPC or and handle the AI ML workloads. So that is where your GPU accelerators come into picture. So why are we using GPUs in high performance computing? Because of the parallelism. As I said, we can parallelly do multiple operations. And then there's a high throughput of it. There's up to 800 gigacores now. And then, there's huge scalability as well as the energy efficiency, because GPU cores are less power hungry than the CPUs. So this is just a difference between a normal GPU and a GPU accelerator. I think we have taken most of the points already. Gaming was a specific task like AI, ML, and computing. That is what the GPU accelerators brings about. Now, going back to the car example, we had different units processing different parts of the car. Now, if you have to assemble it, you need to collect all these parts, have some mechanism to collect all these parts at a central assembly unit, and then make the car, right? And that's exactly what is GPU interconnect kind of a concept. We have done all the computations that we wanted. Now we have to collect parallelly, and now we have to collectively make a training model. So that is, you have multiple GPU clusters, because they're dealing with huge amount of data set and then a huge amount of computation. So all these GPUs independently process these data and then there is a collection mechanism. Different collection mechanisms are there. And then you synchronize those collective information, and then to find the final training in model. And how do you interconnect them? So that's when we'll go to the next section and see how do you interconnect them. It's not just about the physical connection, right? It's also about what kind of protocols are used, what's happening at each of the layers to connect these GPUs so that the data handling is computation is properly propagated. So these are the different ways of collecting the collective operations. There are multiple ways of collecting the operations. One of the simplest is all the GPUs give that computed information to all other GPU. That's what we have in AllGather. Or it could also be that it's reduced to a function, and that function output is given to all the GPUs. Or reduce scatter, wherein only the ones that is interested, like 0 is interested in red, only that comes in. So we have different ways of collecting the information. So we're not going to deal with how the GPU synchronizes the information. So this is just one example. As I said, the process, every GPU processes the information, that is, car parts are made. And then they're notified that, okay, the car parts are made. How do you gather? In the example of car, it's all to one. So it all goes to probably one assembly unit. It's notified. And then all the GPUs synchronize, or whoever, if it's all, let's say, single, all to all, then all of the GPUs synchronize on the data that is available. So this is kind of networking that we are talking about between the GPUs itself to achieve to get the complete train model. So again, quiz time. What is a GPU? Is it a general processing unit, graphics processing unit, graphics powering unit, or good processing unit? Okay, so 71% says it's graphics processing unit, and 14% general processing unit. While it's also sometimes told as general processing unit, it's mostly a graphics processing unit. Okay, another question follows. So because it's a mid, we have already spent almost half an hour. So I wanted everybody to be awake and follow the session. So here we have, what is HPC? High power computer, high performance computer, high performance computing, and high post computing. Okay. There's a 50-50 between high performance computer and high performance computing. Well, it's a technology, so it's most of high performance computing, and GPUs are the kind of servers or which fit into this kind of which are capable of doing high performance computing, basically by doing parallel computing. Okay, going next. So why are GPUs used in high performance computing? Is it because it's cost effective, because there's high parallelism? Is it because that's a low throughput, or is it because it's lossless? Yes, it's high parallelism, though it's also cost effective then compared to using CPUs. But the main reason is because of the parallelism that we can achieve. Okay, so let's now bring the second pillar of data center, networking, right? And what kind of networking is it required for achieving for your AI ML workloads? So one is your training network, where we are actually training the models, which requires high compute interconnect of the GPUs and storage devices. And that is referred to as backend networks. And the other is, once the training model is trained, you're deploying the model, let's say on the edge or data center or clouds. That's inferencing what we're doing, and it's called the inference network. So inference networks are the front-end networks which usually connect to your user application. Like, let's say somebody just wants to, in ChatGPT, or you just want to do, ask something. It first comes to the front-end network for inferencing, and while the back-end network would have trained the models. So that is how it is. And if you talk about car analogy, the backend network is all up to the assembly unit where all the assembling has done. And then your front-end network is where it's getting delivered to the customers, right? So these are the multiple networks for training. As I indicated, we have the GPU backend network, and the most of the traffic there is servers to servers. The GPU servers need to talk to each other, and that's east-west traffic, the huge amount of east-west traffic. They also talk to the storage devices there. And then once we have the inference network, which is for front-end network, where usually we have the east-west traffic, right? Apart from that, we also have a management network to manage all of these stuffs. So going to the infrastructure itself, how is it different from the traditional? Why can't I use the traditional data centers that's been there for ages? And is it required for me to upgrade those to something new? So let's see that, right? What is the main requirement? The answer is, first we need to know what's mainly required by these AI ML workloads. So we definitely need higher bandwidth. Gone are the days where it is 10, 20, 100 Gbps. Now we are at 800 Gbps, a lot of bandwidth there because we're talking about a lot of data training. And it should be lossless, because every time, let's just assume, right, when you're computing, when you're doing the matrix multiplication, one of the data is not there, it's not available. So you just have to wait for that to retransmit, get there, and again complete the computation. So that's a huge amount of time for job completion. So you just can't afford that. You need a lossless network. And of course, you also need a congestion management because it's huge amount of data that's going up and through these servers. And in terms of inference requirements, of course, low latency is one of the key requirement, and because you want to predict, especially in things like, let's say, finance and health departments where they inference using this inferencing requirements, it needs to be pretty fast, and you can't afford a latency there, right? So this is just a depiction of the same thing, information, and in a tabular form, and how is the data center, that is the modern data centers, able to cater to these things. Is a solution that we have. For latency, we are actually coming up with new ways of protocols and new technologies. That's RDMA. And then we have to handle the network losses and better congestion management. We have various protocols again. Bandwidth, as I said, ASICs these days are coming up with really huge, very high power, high speeds. And we also need to have better management so that you have a better visibility into the system. So let's just see how are we going to handle this step by step, right? In the traditional networks, if you see, if one Ethernet NIC, that is like your Ethernet port, needs to talk to another Ethernet port, and you have an application running in server A, and server B wants to is consuming or is asking for that information, it has to go all the way from buffers on the application to the transport driver, and it comes to the NIC. So, and that goes back to the NIC, and the NIC then transport layer, and then to the socket and to the application. So there is this, this very fact that there is multiple steps to it makes it, obvious that it's going to take more time. There's a lot of latency involved, right? So in terms of the stack, if you take it, it's basically a kernel. If you say Linux, let's just take Linux. So Linux kernel is involved. Kernel gets a packet. It waits. It notifies the application. The application next needs to consume that by doing a copy to user, copy from user. Those are the usual Linux things that we do. So all of this copying is happening from the memory, from the CPU memory, all the way up to the application, right? So that's the latency that is getting added in the traditional networks. Okay, quiz time. So what are the key requirements for an AI ML workload? Lossless network, lower throughput, lower bandwidth, and higher power. Cool. This time all 100% got it right. I'm not sure if I was only one to answer or everyone did.
There were others.
Okay, thank you. So it is lossless network. We definitely need lossless, higher throughput, and higher bandwidth. And power is always a concern in data center. We need power efficient system. So how do we remove the latency? I think we all kind of know about DMA, direct memory access, that used to be in the CPU, how an application could bypass the CPU and directly access the memory by doing, the concept of direct memory access. Similar, extending that across the servers, there's some concept called as remote direct memory access. So instead of doing all of this, what if the application could directly talk to the, the NIC, that is the information that's there, the whatever is the content, directly pass it on to the NIC, and the NIC again takes that information and directly passes or puts it into the buffer of the application. So that is zero copy networking, and that's the concept that is used to make this all system low latency systems. It's called, and we need a special NIC for that, because the NIC should be able to now directly copy that information from the memory of the application to the NIC and pass it off. And at the same time, the NIC here should be capable of, directly giving that information to the memory of the application, right? So we need a different, it's called RNIC or RDMA NICs. And that is where we are, reducing the multiple copies and kernel to user space kind of interaction. So this is a depiction of the traditional comparison of traditional mode versus the RDMA mode. If I have to just talk about kernel stack here, so it would all go through, the kernel to the network data. And now we're just saying they can talk to each other, similar to how it happens in a DMA access. So that's what is extended across the networks now, across the NICs now. Okay. So now, if just introduce a GPU, because we're not no more talking about CPUs. We are talking that the GPUs will do parallel computing, and if they had to pass data between GPUs, we would not go through that stack and coming to the CPU doing it for you and all that. We're directly bypassing all of that and goes from the GPU memory of one side to the GPU memory of the other side through the RDMA technology. And the way this works is that the application has to first say memory registration and say, this is my piece of memory that can be directly accessible. It gives that information to the RNIC. And then there's a connection that is set up, like the way we have TCP IP connections, or when you do a socket connection kind of a thing, right? Open, close. There's a different transport protocol. We'll get to that after this. And then once the connection is established, whatever is the data, start, it is sent, you request for it, and the data is sent across this RDMA over the Ethernet network. And then once we have the information, the NIC is going to tell to the application, there is information, you can just start, using it. So that's how this whole RDMA works. So yeah, I mean, just a comparison between RDMA and the traditional, as we have already spoken, there's no involvement of CPU in case of RDMA, making it a very low latency system, and obviously giving you a higher throughput. And there's no kernels involved in this whole process in the RDMA. Now, what are the transport protocols available, right? We said they have to connect, after the memory registration, they need to connect and they need to start talking. So what is a protocol that's there available today for this kind of communication? So we have 4 solutions. InfiniBand, that is primarily from NVIDIA. And this actually requires you to have an entire different native transport layer. And we have Rocky V1 and Rocky V2, which are converged to work on the existing Ethernet protocols itself. One is on the layer 2 and another on the layer 3. And the other is IVARP, which uses the TCP IP. So if you want the protocols to start using RDMA and do a remote direct memory access, this is how each of these protocols have their stacks. So let's have the application here. And for IB's InfiniBand, they have a different transport network link layer. It's completely a different network stack. Whereas Rocky V1 and V2 use the existing Ethernet with UDP and a network layer and a transport protocol that is very Ethernet oriented. Okay. So InfiniBand, as I said, it's from NVIDIA solution. It uses right from the physical layer all the way to your network stack, transport layer. It's a completely different stack. The NICs that are used are also custom. They are not your normal Ethernet NICs. They are different, and the links are also different. The network is completely different. So if I have to use InfiniBand, I cannot use the existing Ethernet-based data center. I have to develop a completely new data center, which with new switches, new NICs, which would go by the InfiniBand stack, right? And the main thing here is a centrally managed. So they have a subnet manager, which takes care of centrally managing the entire interconnect of the GPUs. And they also have to make sure for congestion control, they have something called as credit mechanism. So once we have a number of packets sent, it advertises what's my buffer size and how much the receiver can consume. Only that many packets are sent by the sender, And then when there is a credit release mechanism, after it is released, the sender can again send that many number of packets. So there's some sort of a congestion control, which is again very specific to InfiniBand. So now, InfiniBand being very proprietary and a new data center, what is the solution? How can we actually go ahead and leverage the Ethernet to do it? And that's when the Rocky came into a picture. Rocky V1, that's a Rocky is basically layer 2, and Rocky V2 is layer 3. That is, we can also do routing functionality. This is again high performance, low latency over the Ethernet itself. It uses UDP as its transport, and everything is a standard IP protocols. Then the InfiniBand RDMA is actually embedded into the payload. So we'll see this is how it looks like. As said, the same concept of RDMA is just a protocol. How they connect is through the Rocky V2 transport protocol. So this is how the header looks like. So if you can see, it's embedded into the IP header itself, the normal header itself. So the IP header is going to say that this is a UDP, UDP follows me. And the UDP header is going to say that this is a special, a new type Rocky V2. And then this is your entire GPU-based payload, which is just carried, right? So this is a Rocky V2 is basically RDMA over the converged Ethernet. So we are doing RDMA now with Ethernet as your underlying protocol. So with this, it becomes an advantage here is that you are able to use the existing network. If, of course, the NICs have to be RNIC, but the switches and the networks that's there used can be continued to be all your Ethernet-based switches. So here is just the difference between the two. As I said, for InfiniBand, everything right from the physical layer all the way up to transport is all native InfiniBand, and both of it is used for AML. And the way it is, at least for now, the way it is emerging is for your backend networks, which are kind of for training models, and a lot of companies are big companies are investing in that. They're building, they're going with the InfiniBand solution, and your front end networks, which has already been deployed, where you're you're connecting to your internet, continues to be your Ethernet, and that's where Rocky V2 is being used. Apart from these, there's another player. It's actually they're trying to standardize all this and come up with new ways of making this communication, and that's called UEC. It's Ultra Ethernet Consortium, and it's just as we speak, I think they're just releasing their first standardized document in this month. And so yeah, there is the main important thing is it is standardized. So all your switches, the Ethernet switches, can go and apply these standards against the InfiniBand, where most of it is not standardized, right? And with standardization brings the flexibility. Okay, quiz time. I know there's a lot of concepts that's coming in, and I'm just throwing these balls, but let's just get a landscape view today. So what is RDMA? Random direct memory access, remote direct memory access, remote demanding memory access, rapid data movement access. Well, 60% remote direct memory access, and that's the correct answer. So what is NVIDIA's solution for RDMA? Rocky V2, IRAP, InfiniBand, Rockband. Okay, that's just for fun. Okay, can we have the poll coming up? Okay. it's 40% say InfiniBand and another 40% say it's Rocky V2. And the NVIDIA solution is InfiniBand. The Ethernet solution is Rocky V2. So the correct answer is InfiniBand. Okay, so now we have all had it. We've seen how the backend networks, that is how the cards were all, we had different units making different parts of the car, and finally how they were assembled. We saw that. So let's say there are two types of things, right? Again, that's a backend network. And then we saw how the cards are reaching to the customers and the customers are using those cards, right? So that's your front-end network. Now, while the parts are being transported to an assembly unit, you could face issues of congestion, right? And while you're driving those cars, I picked up a traffic jam here. So that's the congestion that we're talking about. And what happens? The job completion time is highly impacted when it comes to the training networks. If there is congestion, if it's not properly managed, you could have packet drops, and packet drops causing retransmission, and all of this adding up to the completion time. And your inferencing also, when you're in the front-end network, you're trying to predict something, you're trying to, generate something or make some decisions. There could be congestion, there could be other traffics also on the network, right? This is not AI, ML is not the only traffic on the network. So there could be more other traffic on the network, and oversubscription is common. So there could be a lot of congestion. So how do we deal with, how do we make sure that, because low latency and losslessness is very important for both training as inferencing. So how do we, handle this in the networks? So for today, we'll just concentrate on two concepts, two ways of congestion control, which is more used in the Rocky V2 or the Ethernet world. One is explicit congestion notification called ECN, and the other is priority flow control called PFC. So what's ECN? So ECN is basically early detection of congestion. So it's like when you're driving on a road and somebody, who's very close to the, let's say, is seeing that there is traffic jam ahead. So it is signaled, and then he just calls up somebody. He calls up and says, "Oh, there is traffic jam," and he tells to, let's say, the traffic police, and the traffic police then goes back and sends the same information to, at the starting of the road, there's another traffic police. He says, "Okay, there's traffic jam or there's traffic congestion that has started happening on this road, so you better slow down the traffic," right? So the other traffic police, what he does is he makes sure that he slows down the traffic on that road, or divers, asks the cars to divert and take a different route. So that's exactly what ECN does. So when it sees that the congestion, let's say a switch is seeing that there is congestion developing, instead of going to, it's proactive in nature. So instead of dropping the packet after complete congestion, what it does is it notifies to the receiver end saying that there is a congestion that is building up on my network. And see, that's called ECN. And then what the receiver does is he sends a congestion notification frame. It's completely different packet, it's like a signal telling to the sender, look, there is a lot of congestion that is building up in this particular network path. You better slow down the traffic that's coming over here. So that's the kind of way the ECN works. So it's just a same thing explained over here. So let's say host A, host B are sending packets, and one of my switches here starts seeing that there is congestion building up. He sends it to this host X, and then the host X, seeing that, flashes a specific CNP, that is congestion net notification packet. He just sends it all the way to these two hosts, host A and host B, so that they can slow it down. So this could also be a particular traffic itself. Like let's say you have different lanes. Let's say we have different lanes for trucks, we have different lanes for cars and bikes. I know it doesn't happen here, but let's assume it's a very good country and there are such kind of different lanes for different kind of traffic. And then I see that there are a lot of congestion building up on the car lane. So only the car lane is splashed back so that the cars can just slow down. The rest of the traffics can continue to move, right? So that's how the ECN works. So now the priority flow control. Priority flow control is slightly different in the sense that the pausing is done step by step. There is no notification sent directly from a host to another host. So this is like saying you just call up your friend who's behind you and say, look, there's huge amount of traffic here. You better slow down. And then he calls another friend behind and tells the same. So it's just passing the information from one node to another node. So same here also, at layer 2, they use COS, and layer 3, they use DSCP bits to say which queue is being congested, right? Like it's like, for example, on a toll gate, we have different lanes for two-wheelers and four-wheelers, right? So here it's my queue. Let's say my queue here in this example, I'm host A and host B are sending the packet, and I see that my queue on the box that LX is building up, which means I know I cannot handle more packets. I kind of send a pause frame all the way to S1. So now S1 starts holding the traffic, and S1 starts holding the traffic and passes it down to the other two hosts that is sending when this guy's buffer starts filling up. And finally, once these thresholds are also reached on these two switches, they start sending a pause to the host. So it's like point to point, we are sending a pause. And finally, once it has reached the host also starts slowing down the traffic. So this is how we are making sure that there's no congestion and there's no packet, when we are controlling the congestion, and we are making sure that there is no packet drops that happens on the network. So a quick quiz time. Now, so what is one of the main challenges of AI network? Conflict management, congestion control, control unit, RDMA.
Bhargavi also doing a quick time check.
Yes, I'm almost done. Yes.
Right.
Yeah. Okay. Well, I'm glad 100% says it's congestion control, and I'm also glad that we are, still alive in the session. Okay, just for completion, let's just take the storage, because this, again, as I said, is a big area by itself. Storage devices where all your data, two things. One is the data is residing for training models, and the other is the trained models itself residing on the storage devices for inferencing. So that's where your data is. And when you talk about data or storage devices, it's how fast you can access and do a read write into these memories, right? So, and the speed is definitely the most important. And we use solid state drives called SSDs for these rapid access. And the latest technology that's out there is NVMe, non-volatile memory access for Express, so for storing all these training models and the inference for inferencing. So quick recap. Traditional networks are the north-south traffic, which is basically internet traffic. And the AI fabrics that we're talking about, there's a lot of server-to-server communication happening. TCP-based can't be used because it adds up a lot of latency. You need to have specific. That's when RDMA-based communication came in. And it has to be non-blocking and lossless in nature. While your traditional networks continue to use CPU as their servers, the AI fabrics have started using GPU, TPU, that's TensorFlow related processing unit, as well as CPU for final convergence of information. So in summary, what did we learn? We learned that data center is 3 pillars: compute, which consists of servers, and for AI ML workloads, the compute is basically going to be GPU or GPU accelerated version of it. specifically to do all these mathematical computations. And we also can't just do it with one GPU. We need to have an interconnect of GPUs, right? And we saw how is that interconnect or networking achieved. We are now having two types of network coming into picture. One is the backend network, where all your AI fabrics, GPUs are interconnected, GPU to storage is interconnected. And we have, which uses InfiniBand, Rocky V2. And we also have front-end network, which is which can still continue to be your traditional networks, which uses your Ethernet, right? And then different types of storage, specific for AI needs, because you need to have faster access to these memory contents, to the data. STT and NVMe are in place. So with that, I come to the end of my content. So we have another couple of minutes. Any questions you could ask me, you can put it on chat, or I have my LinkedIn. You can always post your questions there. We could, as I said, each of these concepts are by itself very deep. I have just tried to touch upon these things today and give you a landscape of or the terminologies that's there for AI ML infra. So quick feedback, how useful was the session on networking, and how was the overall presentation? And also, do you want to learn in depth? So please rate. So I'm hoping to have all of you answer this.
We'll have a message in the chat saying thank you for an informative session.
Thank you. I know there's a lot of concepts.
It was a lot of concepts, and they were slightly complex, but you broke them down and made them so relatable. And I think that's that is a talent in itself. Yeah.
Thank you.
You see another message from Divya as well. We love and appreciated their efforts.
Thanks.
Okay,
thanks,
I'm going to end the poll. We have almost all participants responding. Could you please have a session on technical program management related to this? Is a request from Anu Dwarka. Would like to learn things.
Okay.
Results for you, Bhargavi.
Okay. Thank you.
Anupama said it was a very interesting session. So I think all in all, it has been a great one. So thank you for your time, Bhargavi. We will be in touch, and if there are any follow-ups for everyone here, we've already said that this session will be recorded and put up on our YouTube channel. So we'll see you there. Thank you again. Have a good evening, everyone. Thanks, Bhargavi.
Thank you. Thanks a lot.
Thanks. Bye.
Bye.